So before we talk about double integrals and going into specific problems, I think most, if not all of you guys are familiar with like for loops when you're coding or something, right? And and so I just want to think of like how we can create a for loop to find the area of this square. So um we go from x equals 1 to x equals 2, and then from y equals 1 to y equals 2. Well, one way you can do it is, because what a for loop is it will iterate over a piece of code a certain amount of times, right? And you get to dictate how many times it does that. And so I will say that for x equals 1 to 2, and I'm simplifying the syntax because obviously I'm not trying to teach computer science right now. I'm just trying to show you something that's kind of interesting. It'll make you understand where double integrals come from. So for x equals 1 to x equals 2, we can set a dx. Right? And so this is that red thing over here. This will be dx. And what this does is it'll go across a rectangle this way from x equals 1 to x equals 2 and be setting a dx. And so once we set that dx for y equals 1 to 2, we want to add dy's. And then once all that's done, once we add up our dy's, we want to do our my bad, dx times. Okay, so what I'm saying here is that we go across our region with dx's, right? But we go across it once, we set a dx, and then we go across the y a bunch of times, add up a bunch of dy's until we hit y equals 2. And then what that creates is a rectangle. And then once we find the area of this rectangle, we go back to the start and do it over again with another dx. So now we would go to the next dx over, and we would create another rectangle. Does that make sense? And then we would just do that over and over again. We would go over and just do it the whole way through. And then we add up those areas of the rectangles and we get our total area. Does that make sense?
Yes, it makes sense.
Okay. And so it's also, so in the context of infinite sums, this is the same as adding up, is it this way? Yeah, it's this way. Actually, let me color code this. That way it'll make more sense. Okay, so this is the exact same thing, right? First, we find a dx. We start at 1 and go to 2, right? That's why we have the 1 on the bottom and the 2 on the top. We start at 1. We set a dx. And then we go into our inner integral. And then we add up a bunch of dy's. And then once we finish that infinite sum, we just multiply them together. We multiply these together. So right, this is our multiplication right here. This integral times dx. So that's all that double integrals are, and that's all that integrals are. You can think of integrals as just like a really complicated for loop, right? And so we can flip this, right? And we can do horizontal rectangles as well. Oops. I'll just hold on. So we can do instead. All right, so I want you guys to help me create this for loop now. For the, let's do a horizontal rectangle. And we're moving this horizontal rectangle. We're sliding it upwards. I'll start with the first piece. So what will we increment our outer for loop?
By y's?
Yes. So what y would we start with?
1 to 2?
Yeah. We find our dy. And then once we do that, we do another for loop, right? So now that we found our dy, we do our next for loop, which would be
Dx from 2 to 1?
From 1 to 2 as well, actually.
From 1 to 2.
Right? Because if we did it from 2 to 1, our dx's would be negative, so you just get a negative answer. But yeah, so from x is equal to 1 to 2, we'd add up dx, and then we just do, and then after all of that, we do dy. I just put parentheses f because we have multiple dx's that we all added up and we're multiplying by. And so we can represent this as a double integral, right? Our inner for loop, so our inner for loop would be adding up dx's from x equals 1 to x equals 2, right? Usually we shorthand this by saying 1 to 2, but I'll be more specific. And then we do our outer for loop, right? I guess you can kind of think of it as this as well, but yeah. So we do our outer for loop from y equals 1 to y equals 2. And does someone want to try give me a reason why this has to be on the inside? Why don't we just move this to the outside? We would still be multiplying by a dx and a dy.
You're taking the inside derivative in terms of x with respect to x.
I think I see what you're saying, but what I was looking for was like, if we were in this case, actually, this works as well, right? What this does, let me just write it out. This actually works in this case, right? Because think about it. We add dy's from 1 to 2. That's 1. And then we add dx's from 1 to 2. So that's 1. And so in this case, and then we just multiply those together and we get our area of our square. And so it actually works in this case. But the reason it doesn't work and we have to put it inside is because, again, when we have more complex, right? Once we get more complex shapes, if we were to take this sector, right, and just add up all our dy's and add up our dx's, that's a Riemann sum, right? Because now it's just we added up our we added up our dx's, our dy, and so we actually found the area of this, right? That's actually just a Riemann sum. And also another thing to think about is we're no longer sliding a rectangle upward, but just finding the area of one big rectangle, right? Here, we're actually sliding a rectangle upward. We're doing this because we first set a dy, right? The nature of for loops is that we find a dy, and then we do this inner for loop before we go back out, right? Before we start from the top again. And so that means that we set a certain dy and we find our dx's along this certain dy, right? We pick that dy. Do you guys see what I'm trying to say here? I kind of ran out of colors, but we found this dy. Here, we set this specific dy, and then we incremented our dx's across. Does that make sense?
Yep, that makes sense.
Okay. So that's all that integrals and double integrals are actually. And so yeah, so it's honestly really simple, right? And all you guys did, remember earlier when you guys would instead, you would just take, you would basically do this inside for loop without the integral, right? Instead of saying this, you would just say, oops, I don't want to erase it. Instead of saying this, when you did your singular for loops, you would just say 2 minus 1, right? Multiply that by 2 minus 1. And it's the exact same thing. You're just skipping the second integral. So, because, I mean, this is the same thing as just 2 minus 1. So you're just skipping the second integral when you guys used to find area with just one integral. And so I hope that makes sense, right? Because, yeah, I hope that makes sense. It took me a little bit to figure that out specifically when I was doing double integrals the first time. So I just wanted to give you guys a little boost over there. Yeah, so I don't know. Do you guys have I can talk let me actually talk about one more thing first as well. Give me 1 second. I gotta go AFK for a little bit.
Got it.
Okay. So what was I gonna say? Okay, so now there's a question of I'm gonna keep this side. I won't erase that side, but there's a question of now, what about when you're having something inside your integral? Like this, right? I don't know, 1 to 2. I'll just do this again. Right? All you're doing in this case is you're actually just doing a triple integral. Remember how we said you used to shortcut areas like this just by doing right? Or you would do or you would another way to think about it, I guess, f of x dx. Here's just another function, and you're just shortcutting your third integral. This is the same thing as a triple integral. And so we can think about this. This will give us a third dimensional number, right? It'll give us a number that represents something in 3 dimensions. And so what people like to do when they represent it, they like to use z, right? Because that's what we usually do for 3 dimensions. And we go from 0 to x squared y. Let me use different colors again, because I'm going to draw this out too. Sure. Actually, yeah, that works. And then from 1 to 2. I'll write out the y's. Y is equal to 1, y is equal to 2, and then this one is x is equal to 1, x is equal to 2. This is the exact same thing you guys do when you have something in the integral, right? You just have 3 for loops instead of 2. And so what this would look like drawn out, I think you guys might already be seeing this, but what it looks like drawn out, I don't want to erase this just because since I use the same bounds, this is actually I don't know what z equals x squared y looks like, so I'll just pretend it's some. That was terrible. Hold on. Let me. Definitely doesn't look like this. But pretend it's some function above, like 3D function. It would actually this would be your x. Actually, is that the way we do it? I think x is over here actually. X, y, z. So this would be the same actually the same exact thing I drew over here on the bottom. Right? What would that rectangle look like over here? We're doing a dy dx. So our inner loop is dy. Our outer loop is dx. So actually, this is, which rectangle will it look like? Will it look like this rectangle? Or will it look like, it might be hard to see, I don't know if you guys can see that, but will it be this rectangle? Will that rectangle go across the x-axis, be longer on the x-axis or longer on the y-axis?
Longer on the y-axis
Why do you think so?
because our bounds are in x.
Yeah, that's one way to think about it, is that our outer incrementer, our outer for loop is in x, which means that the thing we're incrementing on last is our x, so that's going to be the shortest, right? Because we're just going to pick a singular dx and go off of that. Another thing you can think about is, actually that's probably the best way to think about it, right? Because then we have our outer x, we pick the dx. Oh, I did this way too small, but we picked the dx, right? And then we did our dy's. Next, right? That's our second for loop. And then let me actually show out the dz. So let me erase all this and draw the correct rectangle that we use. So we have our 2D rectangle, and then we actually just, once we have our 2D rectangle from our 2 for loops, when we get to our inner third for loop, we turn that into a really thin, that's not great, but does that make sense? We turn this into a really thin, flat on the top. It kind of looks curved on the top, but it's supposed to be flat. We turn this into a really thin rectangular prism. Does that make sense? Right, because we picked the dx, then we picked the dy. Here, let me actually draw it out to scale here.
Yeah, that makes sense. It's like a small dy.
Yeah.
And actually a small dx.
Yeah, so we picked a dx, we picked a dy, and then we picked a dz. We picked a dx, added up dy's, and then added up a dz after that. Yeah, I don't know. Yeah, that works. Does that make sense? This is basically what we did. And
yeah, that makes sense.
And so that's all like multiple integrals inside of each other are, which is just for loops. That's all they are. Okay. So we can move on. I think you guys also did, if you guys want to do questions on double integrals, I can do maybe a few, and then we should move on to the other stuff. You guys also have, what do you guys also have? Arc length and surface area. We can do those as well.
Yes.
So I don't know. If you guys have questions on this, we can do this. Actually, one last thing. This is why I did triple integrals in the first place. The reason we can actually move the x squared out into our x loop, and the reason for that is that since we picked a dx, this x squared in the context of our current dx is not going to change whether we have it inside our second for loop or outside our second for loop, right? If you think about it like for loops, I'm just going to go really quick. If we put dx out here, and then we put it here, and then we put dy here. It doesn't matter whether it goes here or here. Does that make sense? So it doesn't matter whether our x is outside or inside, because the context in which we add up our x's or add up our dx's or whatever is not going to change, right? We picked an x for this whole loop already. Does that make sense?
So because it's the outside bound, it doesn't matter if it's in the bound or outside?
It doesn't matter. Yeah, as this can go outside all the way up to the for loop that is the same variable, because like let's say I said for random x, right? Just a random x. And then for random, let me put this a little bit farther out. For random y, right? If we put, and then let's say x is equal to 2 times x, right? So we multiply by 2, whatever. And then y is equal to 2 times y, and then we did x times y all the way at the bottom. It doesn't matter whether we multiply x by 2 inside our second for loop or our first for loop, because we picked the random x already, right? And we're still incrementing inside of that for loop, right? The only thing is we can't take it outside of this for loop, because then it doesn't pick it doesn't get the context of whatever random x we picked. Does that make sense?
Yeah, that makes sense.
Okay, that was my best I could explain. And same thing for y. That's why we can't, in this case, we cannot move y outside, because then it loses the context of this for loop, right? That's the equivalent of, if you think about it in a single integral, that's the equivalent of saying this is equal to this or something, right? Obviously it isn't, because then you lose whatever context you needed for your dy, and this expression becomes meaningless if you do that. So yeah, that is everything about double, triple integrals, all of that, conceptually. So I will erase this. Okay, do you guys have questions on, like, specific questions, specific problems, or should we move on to the next thing?
So we have a packet on double integrals, and I think he went over some of the example questions. But can I send 2 pages, and can you go over one problem from each page?
Yeah, I can do that.
Got it. Sounds good. I'll send.
Okay, while she's sending that, actually one thing I wanted to make sure you guys know how to do. Let's say we have, I'll just do this really quick problem. We're not going to actually compute the double integral. I just want you guys to set it up, because that's also important. Okay, so if you guys wanted to compute this area, what would the double integral look like? How would you express a double integral? Well, first thing we should think about is the dy here, or is it dy dx here? I'll just write it out fully. Is it dy dx, or is it dx dy? Because if we think about this in the context of for loops, right? We want to increment across our dx on the outermost layer, because we want to pick a dx and then move our dy's off of our certain dx. And so the outside would be our dx, and the inside would be our dy, right? We pick a dx in our outer for loop, then do the inner integral to get this over here. And so that's one part of it. So we know that. And since it's only a two-dimensional integral, there's nothing on the inside here. Doesn't matter. And then we need to pick our bounds. So since this is a dy integral, we're going to be incrementing across two y's. And then since this is a dx integral, we're going to be integrating across our x's. So then what would the bounds look like?
For y, it would be x squared and 0. So 0 to x squared.
Yeah. Because our rectangle, we're adding up dy's from 0 all the way up to x squared. And then what about our dx's?
Which problem is this?
Oh, it's not a problem. I just needed to make sure you guys know how to pick the bounds on a integral. So then what would our x bounds be?
0.
0 to 1. I think that's what you said, right? Because we first pick a dx,
Yeah.
we pick a dx, then we compute our rectangle across that dx, right? We do the inner dy, multiply it out. And then we go to our next dx over, we compute another rectangle. We go to our next dx over, compute another rectangle. We just keep doing that until we finish the integral. It's very computational when you think about it. Okay. Yeah, I feel like I see a few people join. You kind of missed the whole initial part with me talking about for loops and stuff, but you guys can go back in the video for that. I'll post it really soon because it's really cool how it's pretty much you can think of it all in for loops, which is kind of cool. Okay, so which one of these did you want me to do that you sent?
You can just pick any of the problems from the page. We can do one per page.
Okay. Sketch. Okay, so you guys are sketching it. He didn't make us do that last year. So let's do sketch in 3 dimensions. Is that what it means in R3? We can do that. Let's do, trying to pick a good one. Let's do number 11 on the first one you sent. Okay. I forget what this one is, the x, right? And this one's the y. I always forget.
Yeah.
Okay.
X, Y, and Z. That's correct.
Okay. So let me write this integral out here. So dy dx from x squared to 2x from 0 to 2. Okay. So we can think of this computationally again to make this easier. But one thing I would recommend before we do that is just we know what our bounds are, right? We can just graph out all these things and check what our bounds are. So y is equal to 2x. That's like this, I'd say. You know, I'll do it in a lighter color. That way it doesn't mess with it. So that's y is equal to 2x. And then y is equal to x squared. From 0 to 2. Okay, so where does this intersect? This intersects at 2. So it's, yeah, that's perfect. So it goes, so it's this area over here. From 0 to 2. Okay, so now if we think about this like a for loop, right? We picked a dx on the outside. So we picked a dx, and then we added up dy's on the inside, right? Actually, since there's some new people here, I'll actually just write out the for loop. That way, hopefully you guys can see what I'm talking about. So Okay. So our outer for loop, right? This is, sorry. I'm trying to color code this so it's easy as possible. So our outer for loop, right? This is our outer for loop. Is from x is equal to 0 to 2. We picked a dx, right? I'll just put a random dx here. I'll put it over here, right? And then we moved on to our inner for loop, right? From x squared to 2x, we added up dy's. So added up a dy, added up another dy, added up another dy. Okay, we hit 2x, so we stop. And then once that's done, we get the area of our rectangle. And then we move on. We go all the way back to the beginning. Should switch my color. We go all the way back to the beginning and find a new dx. And so what this looks like is we're taking a rectangle, right? Start drawing it out a little bit, and we're sweeping it this way, right? Across our x. Because we picked the dx, added up the dy's, right? Picked the dx, added up dy's, found the area, and then moved on. So that's what it looks like sketched out. Do you need me to do it? Because it just says sketch, but I don't know if you guys need to find it as well. Does that make sense? Is there any questions?
How do you know the graph of y equals x squared goes that way?
I mean, y equals x squared in our 2D plane looks like this, right? And this is our x and our y. So I just kind of mapped it out. Does that make sense? Actually, it's kind of poorly drawn because obviously it doesn't go asymptotically like this. It goes more like, hold on. Goes more like this, if that makes sense. But yeah, that's how I know. And then obviously, since there's no definition for z, these move upwards. I don't know if he needs you to draw that, because it always looks messy to me, but right, those are upwards because you can pick any z.
Oh, that makes sense, because usually it wraps around the y-axis, so that's why it's drawn like that.
Yeah. Okay, so I think that's good. We'll probably do plenty of computation. Oh, you're only sketching. Okay, so he makes you guys draw the rectangular strip, so that's great. Because I didn't think, I don't know if he made us do that last year, so I didn't know. Switching order of integration. Yeah, let's do these. These ones are important because it makes sure that you truly understand what you're doing when you do the double integrals. Okay. So let's do, I'm going to skip the second page because it's very similar. I'm just going to move on to switching order of integration. I'll do number, I don't want to do a super easy one, but I'll just do number 4, and then I'll do number 9 on the page right after. Okay, number 4. Number 4 is from x equals 1 to x equals 2. I think these are, oh wait, no, it's y equals 1 because that's on the outside. So from, actually I'll just draw it. Okay, dx, dy from x equals 3 to x equals 4. From y equals 1 to 2. Okay. So we know our bounds. Let's draw that out. X equals 4 to 3. It's like here, 4, 3. X equals 4, x equals 3. From y equals 1 to 2. Okay. So does someone want to tell me if these are either vertical or vertical or horizontal rectangles? Oh, and then yeah, we can do number 7 on page 4. Let me see which one that is. where was it sent? Page 4. Is that the xdxdy? I can do that one right after this. Okay, so which one is it? Is it a vertical or horizontal rectangle?
Horizontal?
Yes, it is. So the reason for that is we have our inner and our outer, right? And so we do our outer, we pick a random dy, or not a random, we pick a dy starting from 1 to 2, and then we move on to our inner, which will slowly go across. I mean, obviously not slowly, but it'll go across, and it makes a horizontal rectangle. Okay, do you need me to do it as well? I can do it as well.
Yeah, we should do it.
Okay, so let's do our inner integral. So that'll be x. Oh, that'll be x from 4 to 2, which is 2. And then that's 2 dy from y equals 1, put 1 to 2. 1 to 2, so that's 2y from 1 to 2. Other way, whoops. 1 to 2, so that's 2 times 1, which is equal to 2. Does that make sense? We do our inner integral and then we do our outer integral.
Yep, that makes sense.
And I mean, you could also do it the other way if you want to be weird, and you could call this a, right? And then you do it. It's, yeah. Actually, I don't even do that. Yeah, you can do that. Actually, no, you can't do that. It only works in this case because, again, it's a rectangle, and when I was talking about the for loop, how you could split them up earlier, but that's just because this is a rectangle. It's a special case, right? So I could, because essentially if we were to do them apart and then multiply them later, we would just be finding a big singular rectangle. In this case, since our shape is a rectangle, it works out. But anyways, okay, so that's that. I'll move on to number 7. Okay, number 7. Okay, so that's okay. There's a lot of ways to think about this one. From x equals root y, I find that it always helps to put the like x equals y equals on our bounds. I don't know. It just helps me out because yeah, x equals y minus 2. That way I'm really clear on what my functions are exactly, and then x is or y is equal to 2, and then y is equal to 4. Okay, so as I was talking about earlier, you can turn this inside. Wait, let me do that in green. You can do the inside of this as another integral, and then it becomes a 3-dimensional integral, right? From 0 to x. So z is equal to x, z is equal to 0. And so you can draw this out. You can sketch it out as a... Oh, were we supposed to switch the order of integration on the other one?
Yeah, I think we were. It says switch the order and then
Oh,
integrate.
whoops. I forgot to do that. I'll do it on this one. It's...
Got it.
Yeah, okay. So, yeah. So you can do it as another integral, but because it's given to us, I'll just leave it as is, right? And it becomes a 3-dimensional integral, but yeah, that's fine. I'll just leave it. So, yeah, so let's draw out our bounds and figure out what kind of rectangle we're doing. X is equal to y minus 2. That's y is equal to x plus 2, so that's like, it's like this. And then x is equal to root y. That's y is equal to x squared, so that's just the positive side of x. So something like that. And these, I think these are both the same at y is equal to 4. So 4 comma 2, I think is the point. And then it goes from 2 to 4. Okay,
What
well,
problem is this? Sorry.
this is problem number 7 on page 4, I think. So 2 to 4,
Thank you.
and then we know that 4 is this intersection point, so that's x is equal to 4. Okay, so that's this area. Is this a vertical or horizontal rectangle? Oh, and also just to note, the reason we're disregarding the x, right, is because this is represented as another integral. So I could actually have drawn this whole thing out in 3 dimensions and done it that way. I don't want to do that, so I'm not going to do that. I did that earlier, I think. Like I don't think most of the people who were here weren't there for that, but you can watch the video for that part. But yeah, so that's the reason we get to just disregard x, because this is just another integral in the 3-dimensional space, which we're not concerned about, right? We can just keep that as is. Okay, so is this a vertical or horizontal rectangle?
Horizontal.
Yeah, because we go on our outer for loop, right? As I said earlier, these can be represented as for loops. So we do our outer integral slash for loop. We pick a dy. Hold on, I'll just dy. So we pick a dy, and then we do our inner integral after we pick the dy, right? Or we start at y equals 2, go to y equals 4. Well, I did this whole thing wrong, actually, now that I'm thinking about it. Yeah, I did. My bad. Hold on. This is not x equals 2, that's y equals 2 and y equals 4. So that is, this is completely incorrect. Hold on. X is equal to y minus 2. X is equal to root y. So this is y is equal to 2, and then I'll do that lower. Y is equal to 4. Okay, so this is actually what we're doing. My bad. So we picked the dy on our outside, starting from y equals 2 and going up to y equals 4. Right, we picked the dy, and then we went across, then we went to our inner for loop, and we went across it with dx's to form a rectangle, and then we multiplied them together, right? There's an implicit multiplication going on here. And that becomes the area of a single rectangle, and then we go back into our outer for loop and do another rectangle a little bit higher up. So it is a horizontal rectangle. Now, that means we need to switch this into vertical rectangles. So vertical rectangles would be, instead of, obviously they're just switched, but
I think you drew it wrong.
did I again?
Yeah, I think the line should have been y equals x plus 2. So it starts from y equals 2, the straight line.
Oh my gosh, yes. Yeah, I did. Bruh. Okay. Hold on. I will redraw it. Okay. All right, and this intersects at y equals 4. So this is 2 comma 4. Okay, that's what got me messed up. So it was what I originally drew. Okay. So it's not that area. It is this area from y equals 2 to y equals 4. Okay, so we already established that these were horizontal rectangles. So we want to turn them now into vertical rectangles. So we do dx. So we pick a dx now, starting from here, going to here. We pick a dx. We pick a dx, and then we add up dy's, and then make an area, and then multiply them, and then move on. So what's our initial x? What x do we start with in our for loop? We start at x equals 0 in the shape. So x equals 0. And then we go all the way to, there's a little bit of a problem because now we need actually two integrals, because we have two different rectangles that need to be expressed in two different ways. right? And so when you're switching bounds, it's not always equal to one integral. Now it's equal to 2. So we'll do this first. Let's do this one first. So we start at x equals 0, go all the way to, this is y equals 2, right? At what place does x equal to root y? Does y, if y equals 2, x is equal to root 2. So this is at root 2. So we go all the way to x is equal to root 2. And then we add up dy's from y is equal to 2, right? This over here, y is equal to 2, all the way to y is equal to, up top here, y is equal to, sorry, this is, the line is y is equal to x plus 2, right? So yeah, right, it was given to us as x is equal to y minus 2, but now we need it in terms of y, so that's y is equal to x plus 2. Okay, so that's our first integral. We need to make a second one. So our second one, we add up the x's starting from root 2. So x, that's the outer one. X is equal to root 2 all the way to x is equal to 2. And then we add up dy's from y is equal to, y is equal to, this is, I should write these out. X is equal to root y. So y is equal to x squared. Implicit domain restriction of x is greater than or equal to 0, but it doesn't matter since we're only working in this quadrant anyways. So y is equal to x squared all the way to y is equal to x plus 2. Okay, so we successfully switched the bounds. Do I need to compute it out? I can do that as well. Does it make sense? I kind of went through that quickly, but does it make sense what I did? I can answer questions right now on this before I actually compute it.
Where did you get the x squared from?
So
Oh,
yeah, because
I think I get it. Yeah, because
we have x is equal to root y, right? And if x is equal to root y, y is equal to x squared with the implicit, this is important, the implicit domain restriction that x is greater than or equal to 0. But since our rectangle is in that domain anyways, we can just ignore this in this case, right? So these are equal for our use case. So we, and since we need it in terms of y, right? Now that we're adding dy's, we need it in terms of y, right? We need to go from here to here. So we need this line in terms of y, and this is y is equal to x squared. So that's why it's on the bottom. Does that make sense?
yep, that makes sense.
Okay. So are there any more questions so far? Again, I kind of went through that quickly. It's my bad.
Wait, our original like integral had the integral of x, right? Do we put that?
Had the integral of x, so it has. Are you saying that? So we have an integral. Oh yeah, we do. Sorry.
Do we need to put that somewhere?
Yes, yeah, I forgot about that. They just go in there, right? Because I don't know if you were here for when I last said it. This is just another integral in the third dimension from 0 to z is equal to x. But since he gave it to you and he just said switch the order of integration, we don't have to worry about it. We can keep it in both, right? That's fine.
All right, thank you.
And I mean, even conceptually, it makes sense why we just keep it in both, because if we were to look at this in 3 dimensions, I'll just be quick with this, right? Z is equal to x squared does not change, right? So we can just split it and put it into both of the different integrals, right? So, yeah. I mean, it doesn't change whether it's in 1 or 2 integrals. Okay, so does that make sense? All right,
Yeah.
I'll move on to, yeah, I kind of went, again, I talked about doing this as 3-dimensional integration separately. I talked about it earlier, so you can go back in the video when I post it if you want to see that, but let me just compute this. So this, let's do the inner integral. Actually, are you guys okay with me erasing the drawing? Because I'm just going to compute it.
Yeah, you could erase it.
I need space. So, do you guys want me to do both this one and this one? I can do both. Let me do both actually. That's fine. So x dx dy from root y to y minus 2, then y is equal to 2 to y is equal to 4. Okay, x dx, x squared, x is equal to y minus 2, x is equal to root y. We plug each of those in. That's y minus 2 squared minus root y squared, which is y. We don't need an absolute value because we're only working in positive in the first quadrant with positive y's anyways, so it doesn't matter.
Isn't the x squared divided by 2?
Yeah, it is. Bruh, I am messing up today. So that's 1/2 dy from y is equal to 2, y is equal to 4. We integrate this, y minus 2 cubed over 3 minus y squared over 2 from y is equal to 4, y is equal to 2, 1/2 of that. So 4 minus 2 cubed is 2 cubed, so that's 8/3 minus 16 over 2, 8 minus 2 is 0/3, so 0 minus 2 squared over 2, so that's 2, so it's 2. So 8/3 minus 8 plus 2, which is 8/3 minus 6, which multiply by 3 top and bottom, we get 8 minus 18 over 3, which is negative 10/3. Oh, and there's a 1/2 out there, so that goes here. So it's negative 5/3. So that's integral number 1. Integral number 2, I'm just gonna erase it. Integral number 2 is this. I'll do each of these separately. I'll do the first one. I'm not gonna write any of the, I'm just gonna try and do it with minimal writing, so I won't write out too much. X plus 2, 0, root 2. So that's x squared over 2 from x plus 2 to 2, so that's x plus 2 squared. Oh wait, no it isn't. Yeah, that's a fatal error, because we're integrating it with respect to y, so x is treated like a constant, so it's xy. So it's x squared plus 2x minus minus 2x. So that cancels out. So it's x squared dx from 0 to root 2. So that's x cubed. There's a 1. There's no 1/2. Whoops. X cubed over 3 from 0 to root 2. So that's 2 root 2 over 3 minus 0. So that's one piece of it. Second piece, root 2 to x squared x plus 2. Okay, so xy, x plus 2, x squared. Plug that in for y, right? Because there's the implicit y is equal to on our bounds that we just don't write. X squared plus 2x minus, in this case, it is x cubed. And then we integrate that with respect to dx, with respect to x, from root 2 to 2. So that's x cubed over 3 plus x squared minus x to the 4th over 4 from root 2 to 2. So that's 8/3 plus 4 minus 16 minus 4 minus 2 root 2 over 3 plus 2 minus 2, I think. So then those cancel out. That cancels out with that, so you're left with 8/3. That is not right, is it? Did I mess something up? Probably did. Hold on. Is it 2 minus 2? Plus 2 minus 4, oh, minus 1. I think that's it. Yeah. Okay, so then these cancel out, so it's 8 thirds minus 2 minus 1 minus 1. So that's still, am I tripping? That's still only 5 thirds. Is it, there should be a negative somewhere. Hold on. X cubed over 3, a cubed, 4. Minus 4, so that's 8 over 3. Minus 2 root 2, plus 2, minus 1. I'm getting 5 thirds. Is there something I'm doing wrong here? And it probably is. But I mean, where would I get a negative? What am I missing? Huh. Okay, let me check this. Let me check my bounds once more. You guys see where I'm going wrong here? I can't tell.
The only thing that I'm kind of think you did wrong is that why did you cancel out the 2 root 2 divided by 3?
Wait, where? Sorry.
On the bottom part. In column pen.
Are you talking about where I canceled them out?
Yeah.
It's isn't it cause you add these together once you figure out, cause like, so basically you have 2 root 2 over 3, and then
Yeah.
you have, here in this case it's 8 thirds plus 4 minus 4 minus 2 root 2 over 3 plus 4 minus, or not 4, plus 2 minus 1. So then that's 8 thirds. That cancels out. So it's 8, and then this is plus 1. So that's 8 thirds minus 1 minus 2 root 3. Or not 2 root 3. 2 root 2 over 3. And then you add these areas together, right? And so those cancel out, I think.
Yeah, that gives you 5 thirds.
Yeah, 5 thirds. But then when we did it the other way around, we got negative 5 thirds. And that's what the answer says too.
Oh.
Oh. Hold on.
I think maybe something's wrong with the equations because I plugged it into the calculator and it gave 5 thirds and not a negative answer.
Yeah, for this, right?
For this integral, yeah.
Yeah, so here's my here's what I'm thinking, right? Because how could we possibly get a negative answer, right? Like, how could we possibly get that out of an area? Well, that means our rectangle is flipped, our original rectangle, and I guess I didn't realize it. So let's look back at our original rectangle. We go from root y to y minus 2. So that's this way, I think, right? That's the way, like, if we were to draw out our original rectangle, see, that's wait, let me just make sure before I say it. Yeah, okay, that's diabolical. So basically what he did was, okay. Is it okay if I erase? I'm gonna erase this because I have it up there anyways. Oh, okay, so here's what he did. So you have y equals x squared, and then you have y equals x plus 2, right? And in our original, right, we start, see, this is why it's really important to think about it in for loops, right? Because we start at this bottom part, which is x is equal to root y, and then we go this way for our, let me see if I can visualize this better. We start here, and then we go this way to make our rectangle. So those are negative dx's, so our answer is negative, right? So I failed to capture that in our switched bounds. I'm just trying to figure out how you would capture that without just putting a negative on the outside.
Well, in that case, can't you just switch the
Oh yeah,
bounds?
yeah. I would just switch these x bounds, right? Does that make sense?
Yeah.
Yeah, so this would be root 2, this would be 0, and then this would be 2. Wait, this would be 2, and this would be root 2. Does that make sense? So that's why it's really important to think about it in terms of for loops and like figure out how you're incrementing your rectangle exactly. Yeah, so that's I can see that, like, I can see that being like a problem on the test that people get wrong, because you know that I would get wrong because I didn't do that. So does that make sense? I can explain that again because this is really important, but does that make sense?
Can you explain it again, please?
Yeah. Okay, so when I started this session, I talked about how you can represent these integrals as for loops, right? Because they're infinite sums starting from one bound to the other bound, right? We're adding up dy's from y is equal to 2 to y is equal to 4. And then we're adding up dx's from x is equal to root y to x is equal to y minus 2. And then we're multiplying them together, right? And so let's think about this in the way that like a computer would do it or something. So I messed it up. Hold on. Okay, I'll just redraw it. So basically, so this is the area we're trying to find, right? What this integral is telling us is, okay, let's start with our outer for loop. I'll rewrite this as a for loop actually, so that it makes sense, right? So our outer for loop is 4 y is equal to 2 to y is equal to 4. We pick a dy, right? Okay, I'm just gonna pretend we're in the middle of our operation and we picked a dy over here, right? Oops. So, we pick a dy, then we have a dx. X is equal to root y all the way to y minus 2. We add dx's. So we started at root y, and then we added them all the way back to y is equal to, or x is equal to y minus 2. So our dx's, when we added them up, were negative. This was a negative value because we went backwards when we incremented. We switched the bounds, right? Does that make sense? So then once we did that and we multiplied our dy at the end to get our final rectangle, multiplied dy times our dx's, right? When we had our final rectangle, it was gonna have a negative area because we added up the negatives the opposite way. Does that make sense?
Yeah, thank you.
Okay. Okay. I just want to make sure that makes sense, just because this is huge. This is probably like I could see this being like a trick problem on the test for sure. So yeah. So that's why. That's why it's important, one, to realize what you're conceptually doing when you do these double integrals, which is literally a for loop. It's literally a for loop. Like, yeah. Okay.
Java APCSA connection right there.
Yeah. So number 9. Let's do should I switch? I think yeah, I feel like I don't have much time. I have to go eat dinner. So I'm going to move on really quickly and let's just do arc length, and cuz I feel like that's a good problem to end on anyways. That seems like okay. So arc length is, let's say we have a function and we want to find the arc length of this function, right? We want to basically have an infinite sum of these DLs, right? And our DLs can be represented as a really tiny rectangle. I'll blow this up, right? So we have a DL, a DX, and a DY. So our DL is equal to DX squared plus DY squared, right? And what we essentially want is a infinite sum of DLs. And so but we don't really have a good way of making the bounds in terms of L. It's hard to conceptualize. It isn't a good idea. So instead we convert it into either X or Y. Let's do X. So X dx, if we divide by dy squared, we get dx over dy squared plus 1 is equal to dl over dy squared. And then, is that what we're supposed to do? Yeah, and then, oh, this is the other way. Let's divide by dx, actually. Sorry. So 1 plus dy over dx squared over dx squared. Or no. Yeah, this is supposed to be squared. Pythagorean theorem. So, and then we take the square root. So dl over dx is equal to 1 plus dy dx squared. Square root the whole thing. And then multiply by dx. So that's, and then we can find it also in terms of dy. And then we increment across our x instead, and we get our arc length that way. Is there any specific problems? Actually, let me go over how that relates to surface area, and then real quick before we do a problem. So if I want to find the arc length of a function, the easiest way to do it is very similar to disk method, right? Where we have a radius, and then we take a cylinder of infinitesimal height, and we just add those. We add a bunch of those, right? But we don't want a filled in cylinder, right? We don't want to add a volume. We want to add a area, right? An arc, a surface area. So instead, we find an R1, we find our radius, and then we do 2 pi r, right? R1 in this case. And then we multiply that by dl. Now, this has always irked me because I've always thought, like, why can't you just multiply by dx instead, right? And then just increment across this way, right? I mean, they're infinitesimally small cylinders, so like this small difference shouldn't matter that much, right? Because then if we were going to use dl here, why don't we just use dl when we do our solids of revolution, right? If we care so much about this small piece. And honestly, I still don't have a good explanation for it, but I think the way I can best explain it is when it comes to arc length, right? Pretend we have a super like exponential function, right? Even if we do a small dx, the difference between our dl and our dx is huge, right? Pretend it's like a near vertical function. It's like that. We could add up dx's, right? If we were going to do our solids, or if we were going to find our arc length, or not arc length, sorry. What do we call them? Surface areas, right? But then our DL is just huge compared to our DX. So we're losing a lot of information. That's honestly the best way I can explain it. Another way I've seen it explained is like, when we do solids of evolution, these are solid cylinders. And so they're kind of continuous in that they're touching each other, versus if they're hollow cylinders, they're not touching each other. So we need to go across this DL so that they're touching each other and they're continuous. And since continuity is really important to integrals, it makes a difference. I still don't, I don't know. I just don't have a good explanation for why it's a DL, but it is a DL. So then, yeah. And then we know what DL is in terms of DX, so that's all that is. So I can do maybe one problem, either arc length or surface area. Do you guys have any specific ones? I mean, if not, I think these are pretty self-explanatory. I think double integrals are the main part of this, but if not, we can end here.
Thank you so much.
Okay, cool. Yeah. See ya.
All right, thanks.